In this lesson, I'm going to continue a lesson I recorded yesterday in which I gave you a basic introduction to U-Substitution. If you want to print the sheet to follow along with these examples, you can go to this bit.ly link right here and you can print it. And yesterday, I went over some what I consider fairly basic U-Substitution examples, and these are the examples that I did yesterday in the first video. And today I'm going to look at a U-substitution problem where your du is a fraction, which can sometimes create what I call the hidden du. And hidden du is not an official term. I made that up myself, so don't bother Googling it to find more information because it'll probably just direct you back to more things made by me. So let's talk about what the hidden du is. And it shows up when your integrand contains a fraction. And in that case, be on the lookout for what I am dubbing the hidden du. And a hidden du is when your choice for u is not a fraction. So you're choosing something for u that isn't a fraction, but the derivative of that u is a fraction. And so I have right here 5 examples of things that can create a hidden du situation. And if you want to take a minute, pause the video to write down these examples underneath these numbers, you can do that. Let's look at this first one. We have a fraction, and I notice that in the denominator, I see just an x. And when you see that, one thing you might want to consider is to let u equal the natural log of x, because if u is the natural log of x, then the derivative of that choice for u would be 1 over x dx. And I don't see a literal 1 over x, but I do have an x in the denominator with the dx. And if you want to see a 1 over x, you can put a 1 right there. And in doing that, I now see the du right here. And the du is the most important part of U-substitution. And I'm going to come back and I'm going to solve a couple of these later, but I'm just showing you what you would look at in order to pick your u and how the du falls into place. If you look at number 2 over here, if you see a square root of x in the denominator, then you might want to consider u equals the square root of x. And I'm going to solve this one later as well, because if u is the square root of x, then the derivative of that choice for u, or the derivative of root x, is 1 over 2 root x. And then I'll put the dx over here. And so I'm looking for that du. I need a 1 over 2 root x dx. I have the root x in the denominator, which is what I want. I have the dx. All I'm missing is a 2, and I can fix that very easily by sticking a 2 down here. But if you ever put constants in your integrand to give you what you want, you have to account for those inserted constants. Just notice that I divided by 2 in the integrand, so now I'm going to multiply by 2 on the outside, and that would complete the u sub, or the required du. If you see an x squared plus 1, you might want to consider u equals the inverse tangent of x, because the derivative of inverse tangent of x is 1 over x squared plus 1 dx. And I have that x squared plus 1 in the denominator. And the same thing for inverse sine and inverse secant. So I'll go ahead and uncover those. And those will substitute out very similarly to the inverse tangent example. Now, in the context of AP Calculus, as of the recording of this video, which is the early stages of 2024, we will not see inverse secant on the AP exam, but I like to show it to my students just in case they see it when they get to college. So let's look at how a few of these will fall into place if we do actually complete the U-substitution. And let's look at the inverse of the example number 2 on the previous page, sine of root x divided by root x. I have already told you that u is the square root of x. The derivative of that u is 1 over 2 root x. And before I do this correctly, I'm going to do one thing incorrectly, just to reiterate a point that I made in the first lesson, and that is that substituting the du first must be done, because there are situations where if you plug the u in first, you may accidentally mess up the problem, and this is an example of that. Because if you're looking at this, u and the square root of x are equal, and so if I make that declaration that u and square root of x are the same, then I could plug in a u for both of those root x's, which will give me the antiderivative of the sine of u divided by u. However, I have not done anything to account for the dx. So there's still a dx, and it's going to be very difficult to substitute the dx out because in order to get dx out, I need a root x in the denominator. When I plug u in for that root x in the denominator, I basically obliterated what I had available to serve for the du. So don't substitute u first. Always substitute the du first. And so I'm going to go back and do that now. And as I mentioned a minute ago, in order to create the du, I need a 1 over 2 root x. So I'm going to put a 2 here, and that is dividing by 2. So I'm going to put a multiply by 2 out here. So if I multiply by 2 and divide by 2 at the same time, I essentially have unchanged or have not changed the problem. It just looks a tiny bit different, but the value is the same. So now as I substitute, the 2 on the outside will stay there. And when I substitute, I need a 1 over 2 root x for the du. So if you want to put a 1 on top, you can. So I have the 1 over 2 root x dx. All of that is going to come out. So I have a fraction. The denominator, along with the dx, that is all coming out to form the du. And since the denominator became the du, I'm just going to stick a 1 down there to hold the place so I don't get confused. Then I have the sign of root x. Now I still have x's left over, so this is where I'm going to plug u in. So I have the sign of u du, and the antiderivative of sine u is negative cosine of u. There is still a 2 on the outside, plus c. I don't know, plus there. And then we will plug the root x back in for the u, so it ends up being negative 2 cosine of the square root of x plus c. So there's your answer for that example. The other one I want to look at, the second one, is the natural log of x all squared divided by x. And I have already mentioned that we will let u equal the natural log of x. The du, the derivative of natural log x, is 1 over x dx. And if you want to, this is adding an extra step, but if you want, you can rewrite the original problem so that you see the du a little bit more clearly. You can rewrite that original problem as the natural log of x all squared times 1 over x dx. If you write it like that, now the du is much more visible. It's not quite as hidden as it was earlier, but that's adding an extra step, and it just takes a little bit of extra time. But I do have the du right here. And once I have accounted for and substituted out the du, then I'll look everywhere else. U is equal to the natural log of x. So I'll replace this natural log of x with a u, which turns the antiderivative if you substitute into a u squared du. The antiderivative of u squared is u cubed divided by 3, or you could say 1/3 of u cubed. And then we will plug the natural log of x back in. So natural log of x cubed, all divided by 3, plus some constant. And there we have the answer to that last one. Or I think that was the first example on that previous page, wasn't it? Going back ever so slowly. Yeah. And then the last one I'll look at is the inverse tangent example, I'm pretty sure. Yep. So we're going to look at this one. And this is going to behave almost identically to that previous example with the natural log of x. We will let u equal the inverse tangent, or the arctan of x. The derivative of arctan x is 1 over x squared plus 1 dx. And so that x squared plus 1 in the denominator is completing that du. So I'm going to grab all of that, the x squared plus 1 in the denominator and the dx. That is my du. I don't like how that box is still around there we go. And then I will substitute anything else out that I can. I still have an arctan x in the numerator, so that numerator will become just the u. And so after substitution, this turns into the antiderivative of u. That replaces the arctan x. The x squared plus 1 dx is the du. And the antiderivative of u du is u squared over 2. It is time for the Pledge of Allegiance over here. All right, pledge is over. And so we did the antiderivative of u, that is u squared over 2, or you could say 1/2 of u squared. And then finally, we will substitute the inverse tangent x back in for the u, so that my final answer is now the arctan, or you could write it as inverse tan x, all squared, divided by 2 plus a c. And there are 3 of the examples from the previous page. And inverse sine and inverse secant are going to behave very similarly to the inverse tangent one that I just completed.